In this section, we shall study a few eigenvalue related problems. When an operator acts on a vector in a Hilbert space, it gives another vector in the same space. Let us consider the equation L acts on cat A, say gives cat B, where L is a linear operator and cat A and cat B are two cat vectors in the same Hilbert space. Usually in a Hilbert space, there exists some vectors upon which, if a linear operator acts, give the same vector with a scalar multiple. Where lambda is a scalar, the vectors which satisfy this equation are called the eigenvectors of the operator capital L. The scalar number lambda is called the eigenvalue of the operator L, and the vector cat A is called the eigenvector. This equation is known as an eigenvalue equation. Now we shall study three theorems. Let us consider the first one. The eigenvalues of a Hermitian operator are all real. Okay, we are now going to prove this. Let us consider the following eigenvalue equation. Where lambda is a where you see this lambda is the eigenvalue of the operator A. A is a Hermitian operator, and the eigenvector is cat A. We know that for a Hermitian operator capital A dagger equal to A. This is the property of Hermitian operator. This is a special property of a Hermitian operator. Hermitian operators are we call self-adjoint. This A dagger equal to A. A is self-adjoint. Now let us take the bra form of this equation. So we take dagger on both sides. And the dagger of a cat vector is a bra vector, we know. And since A is a Hermitian operator, so we can write this. And lambda is a scalar quantity, so its dagger means its asterisk means complex conjugate. Now, taking inner product of this equation with cat A. So we take inner product. Okay, now taking inner product of this equation from the left by cat A, we get this. So this one is number 2. Okay, this one we get from our this eigenvalue equation, this equation. Now if we equate these two equations, equation 1 and 2, we get if we bring the right hand side and the left hand side and take common bracket A, then we get this. But we know the inner product of a vector cat A with itself cannot be 0 for finite cat A. Therefore which gives us lambda equal to lambda star. Star-X means complex conjugate, which shows that lambda is real. That means the eigenvalue of a Hermitian operator are real. Okay, so this is theorem 1. Now we shall discuss theorem 2. eigenvectors corresponding to non-degenerate eigenvalues of a Hermitian operator are orthogonal to each other. Okay, we shall prove this. And let us consider a Hermitian operator A and eigenvectors ket A and ket B corresponding to non-degenerate eigenvalues lambda A and lambda B. And therefore where lambda A is not equal to lambda B, and this is known as non-degenerate eigenvalues. Means we are considering two state vectors ket A and ket B, and when the operator Hermitian operator capital A acts on these and these kets, they give the eigenvalues lambda A and lambda B, and they are not equal. Now, taking inner product of this equation, let's say this is equation 1 and this is equation 2. Taking inner product one with ket B from the left, we get bra B Okay, let us suppose this is equation 4. We take the dagger of equation 2, so the bra form of equation 2 is so we'll have to take dagger on both sides. This means dagger of a cat is a bra, and since A is Hermitian, so A dagger is equal to A, and this is this. But since eigenvalues of Hermitian operator are real, so this. Now taking inner product of this equation, with get A from the right, so if we take inner product of this equation with get A from the right, we'll get now here we had equation, this one is equation 4, and if we let us say this is equation 5. Now you see the left hand sides of equation 4 and 5 are same. You see the left side of equation 4 is bra B A cat A, and the left hand side of equation 5 is also bra B operator A cat A. So the right hand sides of these two equations must be same. So this, let me say equating. Is that which means but you see we have assumed that from equation 3 and that the eigenvalues are different. Lambda is not equal to lambda b. Therefore we have bra b cat A is equal to 0, which means vectors cat A and cat B are orthogonal to each other. Okay. Now we are left with the third theorem. every Hermitian operator can be brought into a diagonal form by a unitary transformation. We shall prove this now. Every Hermitian operator can be brought into a diagonal form by a unitary transformation. We know operators in quantum mechanics are represented by matrices, and so if we consider unitary transformation, we can bring a matrix, a Hermitian matrix, into a diagonal form. Now the proof. Let us consider a Hermitian operator A in the basis vector set ket E alpha runs from 1 to capital N, where capital N is the dimension of the Hilbert space. So we define the Hermitian operator A in this coordinate system. Now if U ket U alpha be the eigenvector corresponding to the eigenvalue lambda A of the operator capital A, then the eigenvalue equation is, okay, let we consider operator A acts on a ket U alpha, gives us eigenvalue lambda alpha and ket U alpha. This is the eigenvalue equation. Let us suppose that this is equation 1. Now let us consider that the unitary operator U, which transforms the basis vector set ket E alpha. Okay, let us suppose this basis vector set becomes a new basis vector set ket U alpha by the unitary transformation. That means ket U alpha is equal to U ket E alpha. Say this is equation 2. And this is a new coordinate system, new set of basis vector. This is old basis. Since ket U alphas are basis vectors, so we can write down the inner product of basis U alpha with another basis U beta is equal to delta alpha beta. Let us say this is equation 3. And we also know that if we have an operator in this basis, say an operator A, and in this basis that operator becomes A prime, and the relation between A and A prime is this. This is we know. Actually, we have shown this before. Let us suppose this is equation 4. Okay, now we consider alpha beta matrix element of this transformed operator. So it's PHY alpha, and then A prime get E beta. Okay, now you substitute for A prime this from equation 4, this one, and you see we know the cat U alpha is equal to when the operator A, I'm sorry, when the unitary operator U acts on cat E alpha. So we can write down this cat U beta. Just instead of alpha, we have here a beta index. Okay, now we have A U alpha equal to lambda alpha cat U alpha. This is the eigenvalue equation that we considered at the beginning. You see equation 1, this equation. So just instead of the index alpha, we have here the index is beta. So we can write down this which is equal to lambda beta is the eigenvalue, which is a constant. So we bring outside the bra G alpha we again use this one, and this is this. But we know the property of the unitary operator U is U dagger U equal to I, identity operator. So we can use here I. And this is nothing but this, and the inner product of a basis vector cat E alpha and cat E beta is this, and this is the delta alpha beta. So we have found, you see, the new or transformed operator A prime is diagonal. See, because of the delta alpha beta is the Kronecker delta, and which is equal to 1 when alpha equal to beta, and 0 when alpha is not equal to beta. So ultimately the operator A prime has been diagonalized. Okay, this is the end of this chapter. I hope that you have understood what we have discussed so far. Things will be much easier for you if you study this again and again.